This video contains some notes for Section 5.5, Applied Maximum Minimum Problems. These types of problems can be broken up into two big categories. Those categories are analytic geometry problems, which we'll talk about first, and then more like real-world type optimization problems. So analytic geometry problems always have some element of taking a function, setting some arbitrary point on it, and trying to find that arbitrary point that satisfies some condition. So I'm going to give you two examples to illustrate what that looks like. So first example, let's find the point on the parabola y equals x squared that is closest to the point 1, 2. Oops, you can't see the edge of that screen there. Closest to the point 1, 2. So we could make it just a little sketch to see what's going on here. So here's our parabola y equals x squared. It goes through the point 0, 0, 1, 1, 2, 4, and it's symmetric with respect to the y-axis. So it looks something like that. And we're interested in finding the point here that's closest to the point, oops, did I say 1? Sorry, not 2, 1. The point 1, 2. So you might think you should just go straight over and it would be the point right next to that with the y-coordinate would be the square root of 2, 2. But that's actually not the closest. The closest you can get is perpendicular to that. I don't know if you remember from, I guess, Algebra 1 in geometry, you would have done problems where you had to find the distance between a point and a line, and it was that perpendicular distance that did it. So we're looking for this point here. Here's our point 1, 2. And here is some arbitrary point on the function. And this is, in all of these analytic geometry problems, this is a key step. It's defining a point on this function to be the point x, comma, you might say you want to make it x, comma, y, but since we know it's y equals x squared, we could make it the point x, comma, x squared. And then we only have one variable. Now, if we're trying to find the closest point here, then effectively we need to think about, is this a maximum or a minimum problem? This is a minimum problem. We're trying to find the minimum distance. So what we need to do is define a function that will give us the distance between some arbitrary point and this, and then find its minimum. So since we're talking about distance, we're going to define our function using the distance formula. I'm going to call this, instead of f of x, I'm going to call it d of x to remind me that this is a distance function. And remembering the distance formula, which is basically just a version of the Pythagorean theorem, we have x minus x, those coordinates, so that would be x minus 1 squared plus the y coordinates. So this is the distance between any arbitrary point on this parabola and the point 1, 2. And we want to find the minimum distance. So we'd like to look at this function and find the minimum. Now, a lot of these problems, this is one of the first sections where there will be problems that we really cannot do without a calculator. How would we do this using calculus? Well, since we're trying to find the minimum of a derivative, the minimum of a function, we could find the derivative, set it equal to 0, and look for maximums and minimums that way. But this, I think, you might just looking at this, it'd have to be this whole thing to the 1/2 power. It's not going to be a very nice derivative, and we might not be able to do it analytically anyway. It might be like a, an unpleasant, irrational kind of solution. It doesn't have a nice form. So, although this is in a calculus course that we're doing this, we're going to go ahead and just graph it and find the minimum, which is much like you did problems like this in Algebra 2. So let's see. I can get that. I think you can see the screen if I put it there. Here, we'll try that. So I want to graph the function, square root of, be real careful with your parentheses, x minus 1 squared plus x squared minus 2 squared. All right, move that back to the center. And we're going to go ahead, go back to my standard window. So here are our distances. It might not be too surprising to you that this looks kind of like the parabola y equals x squared, because as we get very, very far away on the parabola from this point, then the difference between this point and the origin is actually quite small compared to the much larger distance. So it looks kind of like that, but you can see there's our minimum distance right there. So let's go ahead and find that number 3 minimum value. It's somewhere between, looks like it's certainly between 0 and 3, so I'll just type those in. And it's telling me that the minimum happens when x is equal to 1.366, and the actual minimum distance, remember this y value is our function, so this is a distance. Minimum distance is 0.390, rounded to 3 decimal places, which is what the College Board would like us to do. Okay, so recap here. We defined this arbitrary point on the function. We were looking for a minimum distance, so we set up a distance function. We graphed that, and we found the minimum. Paying very close attention to what the information on the calculator screen was. The x value was the x coordinate, where that minimum distance happens. And since we were graphing a distance function, the y value was the actual minimum distance. So back to our picture here for a second. What do these numbers mean? This is the 0.390. That's this distance. And this point would be the point 1.366, comma 1.366 squared, right? That would be, if for whatever reason we needed this, like we wanted to know the actual coordinates of the point, that would be the point. Okay, that's one type of problem of the analytic geometry type. I'll give you one other example. These are the two classic types of analytic geometry problems. And we'll try to do this one maybe without a calculator. Let's find the area of the largest rectangle that fits inside or is inscribed in, you might see that written like that, that fits inside this triangle. I'll draw you a picture of the triangle. We have, here's the point 0, 3, here's the point 1, 0, here's the point negative 1, 0. So connect those, make a triangle. So what do rectangles that are inscribed inside this triangle look like? Well, they look like this, right? We want to find the rectangle of the largest area, so we're trying to maximize something this time. Okay, well, we need to do the same thing. We need to define a point here, some arbitrary point, x comma something. Now the problem here is we weren't actually given a function like the y equals x squared from the last one. So we need to, it's easy enough for us to come up with this. We just need to find the equation for this line, because this point will have to be somewhere in that line. So let's see, that's a line with a slope of rise, -3, run of 1. So it would be the line y equals -3x, y-intercept is 3, plus 3. That's the equation for this line right here. So that means my arbitrary point is x comma 3x plus, -3x plus 3. Okay, now in terms of these values, what's the area of the rectangle? Well, let's see. This would be x right here, right? But this would also be x. So I think the rectangle is like 2x wide and 3x plus 3 high, right? So that means the area of the rectangle is 2x, that's the base, times -3x plus 3, that's the height, and we want to maximize this. So let's see, this looks a little easier than the last one. We should be able to do this without a calculator. So the derivative of this would be -12x plus 6. Since we're trying to find a maximum or minimum, we set that derivative equal to 0. That happens when x is equal to 1/2. So it's somewhat like what I drew it there. So find that, now look, we were looking for the area here. So to answer the question here, we need to take this number and plug it back in here to find the actual area. So what is the area of that rectangle when x is 1/2? Well, it's 2 times 1/2. It's -3 times 1/2 plus 3. Oops. Sorry, let me move that so you can see that whole thing. And that's 1, 3 minus 3/2. That's 1.5 or 3/2. Okay, those are two analytics geometry type problems. Now, the other classic type of maximum minimum problem, I mean, sometimes you're just given a function and you want to find the maximum or minimum, but oftentimes we see this scenario. We could call this optimization function with adding and subtracting factors. So what does that mean? Well, that means the classic example of this particular type of problem is an economics problem where we have, we want to maximize profit. I suppose you could minimize profit, but nobody really wants to do that. And maximize profit. And maybe we know that we have a cost function. The cost to us as manufacturers of producing X items is maybe something like this: 500,000 plus 80x plus 0.003 x squared. Now, if you want to know why would a cost function have this big y-intercept? Well, if you want to go into manufacturing, before you can even manufacture one item, you have to build a factory and get all your equipment and hire people and so on and so on. So this is like a startup cost. And then things are more expensive to make at the beginning, and as you go on further and further, we expect that that cost goes down. And let's say we also have a revenue function. And maybe the revenue is described like this. We sell things at $200 per unit, right? So that means, what would our revenue function be? Well, if we're charging $200 per unit, then we're bringing in $200 for every x, right? So 200x would be our revenue function. Okay, well, given these two things, what's our profit? Profit is how much it costs us. Oh, sorry, excuse me. Let me switch the order. It's how much money we take in minus how much it costs us to produce those things, right? I mean, this is all fine and good to be making $200 per unit, but if it costs us more than $200 per unit to make the product, then we'll be losing money. So our profit is equal to revenue. I'll just abbreviate these. That's a revenue function minus cost. All right? So from a calculus point of view, if we want to maximize something, we can take its derivative and set it equal to 0. So we'll take the derivative. And since this is just subtraction, there's no special rule for that. It's just the derivative of the revenue function minus the derivative of the cost function. And if you are interested from an economics point of view, if you think you might study economics, or if you're studying that now, these things, the derivative of some function like this is called marginal revenue, and this is marginal cost. The derivatives of these are the marginal versions of them. So if we want to max, we set the derivative equal to 0. And we notice the interesting fact that max profit happens when marginal revenue, or in other words, the derivative of revenue, is equal to marginal cost, right? Just moving one of those to the other side. Now, this is a fundamental principle of economics. Maximum profit happens when marginal revenue is equal to marginal cost. So we could set this up. We could just set up this one minus this one and then do that, or we could set up the function from here to find our maximum, either way. So let's go from here. Marginal revenue would be the derivative of our revenue function, so that's 200. Is equal to marginal cost, the derivative of that is 0, plus the derivative of that is 80, plus the derivative of this would be 0.006x. Right? So solving that, we get 0.006 is equal to, 0.006x is equal to 120. And let's see, 6 would go into that 20 times, right? But this is 0.006. I have 1, 2, 3 more zeros there. So there we go. Maximum profit happens when we sell 20,000 units. Right? That's how we maximize our profit. And, really we should check this. Assuming this is a well-defined problem, I think it would be very reasonable to assume that that was the correct answer. But remember, when we set the derivative equal to 0 here, we could be finding maximums or minimums. So we might have to check this and just make sure, in fact, that it is a maximum and not a minimum. All right. Generally, and there's a very high probability that you'll see a problem like this on the AP test. Problems that are like that marginal cost. We can see problems where, I remember one where we have a beach situation and the ocean is eroding sand at a certain rate. So you have like a sand removal function. So this is like sand going away from the beach, being eroded away, and they give you some function there. And then they have trucks bringing sand in or adding sand, some other defined by some other function, and then they're interested in like when is the maximum amount of sand on the beach. It's just like the marginal cost, marginal revenue. So if you wanted to know how much sand is on the beach, the total amount of sand is equal to the amount you have added minus the amount that has been taken away, right? That's kind of obvious, but then the calculus just follows from here, just like our last one. And there are lots of different ways that this can be set up. Another common one is you've got, say, like a concert or amusement park or something like this where people have bought tickets and they're entering some kind of event. So you have the number of people who have entered, and then the number of people who have left. And if you want to know the total number of people in there, well, that's the number who have entered minus the number who've left. And then again, if you want to find the maximum or minimum number of people, you could take the derivative of this and set it equal to 0. So there's lots of ways of setting up this kind of situation where one function is adding some stuff and the other function is taking it away. And the economics one is a classic example of that.